we've been talking about the loop transfer function and the input-output relationship. So we say that if we have our system, it looks like this, and I'm giving you GH and give you this transfer function, you will need to know y over r is going to be 1 plus GH. Okay? If I'm giving you y over r directly, then you can just analyze the system over here as is, for its transient response. So, in the example 4.1 part B, we have something like this. So in order to analyze the transient response of this guy, do I need to find out the closed loop transfer function again? Or this one is closed loop transfer function already? This is already a closed loop transfer function. But over here, what is an order over here? Is that first order or second order? This is third order. Okay? So when we are analyzing those kind of things, how are we going to analyze that? Are we going to analyze that using first order or second order, or we need to find another way to come up with the third order analysis? First order, second order, another way. I think there are only 5 people. Raise your hands. So over here, you are going to use first order and second order method we talked about earlier to do analysis, because we mentioned this earlier, saying that all the systems are the combination of first order and second order systems. But over here, there is one thing important. We need to determine which one is the dominant one. Because this one over here, obviously, is going to be 1 over s plus phi. That is going to be my first order transfer function. You can take the decomposition of this transfer function and put that one part as something like this, right? We're not going to do something like this, but this is something you can separate this transfer function into 2 parts. One is the second order, the other one is first order. Does that make sense to everybody? But when we are dealing with something over here, we are not going to do things like this, because when we are dealing with this kind of transfer function, we are talking about the poles and the zeros. So we're going to analyze the transfer function in terms of numerator and denominator. Clearly, for this specific transfer function, we do not have any zero because we only have constant term over here, which means we don't need to worry about that. But for the denominator over here, we do need to worry about a little bit. So you are going to have 2 denominator second one is so we got poles located at s equals to -phi. That's from my first order equation. And the second one over here, if you do a little bit calculation, you're going to find it's going to be 0.6 plus minus 0.2 plus minus J 3.18. So far, any question? Should be pretty straightforward. Just take the roots of this one and take the roots of this one, then you get 3 poles. Now, the question is, since I'm telling you one of them is going to dominate the system response, based on the calculation over here, can anybody tell me which one is going to be dominant? This one or this one? Keep in mind, when we are dealing with the S domain, what? Which one is faster? Far away from origin or close to origin? Which direction is faster? Left hand side? Right hand side? Left hand side is going to be faster. So when you say left hand side is going to be faster, it means that the transient response is going to achieve 1 faster than the one over here. So by observing the pulse over here, which one is going to achieve steady state faster than the other one? -5 or -0.602?
-5.
This one is going to be faster, right? So when this one is going to be faster, and this is like 8 times faster. So tell me which one is going to be dominate the system, second order or first order?
First order.
The faster one means it's not going to dominate because achieve is steady state faster. So which one is going to be dominant?
Second order.
The second order one. Okay, does that make sense to everybody? So when you are dealing with those kind of system, so like you know what I'm going to do. This time I have 2 girls. So my girls like 8. This is 10 years old, this is 5 years old. You got a cake. Who is going to finish the cake faster? 10 years old. So when you are waiting for my girls, which one you need to wait for? The smaller one, the younger one, or the older one? The older one. Younger one, right? So who is dominant the waiting time? The slower one or the faster one?
Slower one.
Right. So when you are dealing with those kind of things, it's the same. The slower one is always dominant role in the system. Does that make sense? Is that clear? Everybody understand what I'm talking about? Good. So when we are dealing with something like this, for the second order system, this is my dominant force. So when we are doing an analysis over here, we are going to have which means my omega n equals to 1.682 radians per second. And if you plug this number back into this equation, you got your damping ratio equals to 0.358. When we get those two things, what do I need to calculate? Since I'm telling you this is going to be slower one, so what do I need to come up with? Since I'm telling you we need to find out damping ratio, natural frequency, settling time, and peak overshoot. And this one is going to be 8 times faster, which means if you put everything in terms of time series, the second order is going to have this response, the first order is going to have this response. So if you couple them together, this is going to show up. Because this one, even though it's going to be a little bit distorted in the first view, maybe 1 second, but the rest of the system response is going to look like the second order system response. Which means when you have this kind of system, we try to find out the natural frequency, settling time, peak overshoot, and unit step in, and overshoot. We are going to adopt those equations to find out those numbers. Does it make sense? So I come up with my natural frequency, my damping ratio, settling time is going to be 4 over this one. Do not use tau over here because this one is way faster, which is not the dominant one. So we're going to use this one. In this case, this is going to be 6.64 seconds. The other thing we need to worry about is overshoot. Then we're going to use our formula. That is going to be 100 exponential. We're going to find the answer is 29.98, almost 30%. So when we are talking about something like this, first thing you need to worry about is which one is your dominant poles in your system. If this is the one, then we just follow the procedures. If this is the one, then you're going to find out. We're not going to talk about something like this in this class because if this is going to be the dominant system, what are you going to see? This one is still oscillating, so you're going to see something like this. That is going to be first order dominant with a very low damping ratio. But in this case, you cannot say this one is overshoot because overshoot, the definition of overshoot is greater than 1. So in this case, it's difficult analysis. We can only tell the first order system is a dominant system, and that's all. Other than that, we cannot determine anything. Okay? Any questions so far? Okay, then part C. We are given what are we going to do? Is this one relationship between input and output? No, this is just part of it. So we need to come up with a closed loop transfer function, closed loop characteristic equation. That is going to be S equals to. And everybody understand why I get this one? Because it's going to be 1 plus this one, and the denominator is going to be something else. So you just need to put the denominator multiplied by 1 plus 5.5. That is how we get this characteristic equation. Am I going too fast?
Yes.
Yes. Okay. So okay, so in the denominator over here, I got I don't really care about this part because after the numerator numerical multiplication, this part is going to be just a polynomial, right? And in the denominator, you're going to have and this is going to be a polynomial. When we talk about characteristic equation, we are talking about the equation in the denominator. So that is something we need to pay attention to. So this part is going to be this equation over here. Does it make sense? Am I going too fast? No? It's okay? Good. Okay. Okay, is that understandable? Now, when we are doing this one over here, clearly, we're going to have it doesn't matter what you do. You can just use quadratic equation to find out all the answers, or you can do something like this part over here is just a coefficient, so we don't really need to worry about this part. This is the true characteristic equation we need to worry about. Since we need to find the pole, the second order equation over here is where you should solve for your poles. So when you solve for the poles, you don't need to really worry about the poles. With those two numbers, we get our omega n equals to 6.5 radians per second. Plug this one back into this equation, you got your definite ratio equals to almost 0.6. So with those two numbers, we should be able to identify settling time and overshoot. Just follow the formula. Therefore, Ts is going to be 4 over zeta omega n. That is going to give us 1.04 second. For the overshoot, it is just adopting the same equation. In that case, you're going to find the overshoot is about 10%. So those are my answers. Is that straightforward? Any questions? Okay. Now, we talk about the transient response of first order and the transient response of second order. If we want to use those kind of concepts to come up with the controller, how can we deal with that? Because keep in mind, when we are dealing with system response, we are worried about the performance. If you drive a car or you turn on, how many of you are living in dorm? 宿舍. How many of you are living in the dorm? Okay, now? No, it should be about 80%. So in the winter time, you take a shower, you turn on the water, the faucet water. What happened? Is that going to be hot water right away?
No.
Or it's going to be very, very cold, and you always hate that. Okay, so it's going to be very slow. And most of the time, it's going to be approximate to the first order response. Since you now know control system, and you know it's transient response, because the temperature is increasing gradually, not all of a sudden jump to like 40 degrees, right? It's just increase gradually. So what kind of response we're talking about? First order or second order? Probably first order, right? It's not going to be when you take a shower, the temperature is not like this, right? It's more likely to be like this one, right? Unfortunately, this is very slow. So when you try to design the controller, what are you trying to do? you are trying to do something like this. You turn on the, you don't expect when you turn on the water, it's going to be the temperature you desire. You can only try to bring that as fast as you can, right? So we try to design a controller. Sometimes you have no choice but have something like this. However, if you do have some oscillation over here, you try to keep everything into minimum. Okay? So when you try to keep everything into as small as possible, there are a few things you need to worry about. The first one is, what is my settling time? So you try to determine the closed loop system for its tau or this thing. One must be faster, the other one must be slower. So if it's first order system dominant, then you try to minimize tau. If it's a second order system dominant, you try to minimize the combination, you try to maximize damping ratio and natural frequency. Because if this one is maximized, this number over here is going to be, those two are maximized, this one is going to be what? Minimized. Does that make sense? The other thing is, do you want to have your overshoot to be huge or small?
Small.
How small we're talking about? Do not expect it's going to be 1%. We try to keep everything 5%, which means my damping ratio. Okay, so those things are important things you need to remember. We try to keep this thing as small as possible, while we are trying to make this one around 0.707. If it's greater than 0.707, your system response is way too slow. If it's smaller than 0.707, your overshoot is way too large. So you need to keep balance, which means this is always the one we try to do. However, this is only true for the textbook you're using right now and use Ogata's book. If you look into other textbooks, sometimes they prefer to have damping ratio equals to 0.5 or other numbers. That's up to the textbook. But you know what I mean, because you can say, okay, I don't care about 5%, I can tolerate up to 10%. Then 10% is about 0.6. Okay, so depending on how much overshoot you can tolerate, the damping ratio can be changed accordingly. Is that clear? Everybody understand what I'm talking about? Good. Now, another example that we're going to deal with is something like this. This is the basic of controller design. We call it pole placement. We're going to talk about another method using rule of us, but at this moment we just talk about pole placement. I'm going to repeat this method maybe 2-3 times, then we move on to another type. So all we have over here is a first order system. A closed loop system is shown as the figure over here if a PI controller is designed. The format of the controller is GC equals to KP plus S KI over S. Do not worry about PI controller, the term here, because we're going to explain what is a PI controller later in another topic. Just when you are reading this specific problem statement, just know it's going to be look like this. That's good enough, okay? And we want to find out the corresponding coefficients of Kp and Ki. Those two are the design variables we want to design for our controller. So when we design Kp and Ki, we need to fulfill the following criteria. the damping ratio is going to be 0.707. When you see 0.707, how much overshoot are you going to be expecting?
5%.
5%. Good. So you need to keep that in mind all the time. The second one is I need to have my settling time equals to 2 seconds. So when you see this one, you know it's going to be 4 over zeta multiplied by natural frequency. Okay? And the other one is we want to have our steady state equals to 0. This one is another thing. Because what happened to steady state error? It means that when I'm trying to then drive my system, I hope the error can be 0. So when you try to get everything close to 0, it means that your system must have an integrator. Because when we are doing the closed loop control, over here, what do we have? We got error, right? So if you keep error integrating, it means that I try to minimize the error to the minimum. If you got an integrator, which means it's 1 over S in your system, it means that your system is going to have 0 steady state error. Okay? If you got S in your system, it is what? Differentiated. If you got 1 over S, you got an integrator. So they are different type of stuff. When you have an S, you can eliminate overshoot. However, this one is not feasible because you are predicting your system response. So this one is improper. We're going to talk about improper later. But when you try to get 0 steady state error, keep in mind you always need to have integration. Integration. 积分器. Okay. We are having on my GCOS equals to S APS plus KI. That is from here. And I have my G of S equals to Q over S plus 1. For the closed loop transfer function over here, I have G, C, G, 1 plus GC, G. Do I have free integrator? Yes, I do. Because if you multiply this one together with this one, my GC, G becomes what? S plus 1, APS plus KI multiplied by 2. You got a pole at 0. This is something we call integrator. In other words, if you have a pole located at 0, you got a free integrator in your system, then you do not need to use an integrator in your system. Let me slow down a little bit. If your transfer function over here got an integrator or got a pole located at 0, it means that your system eventually is going to have 0 steady state error. Okay? It also means when you design your controller, you do not need to worry about putting the S over here. You can do anything you want to. But if you do not have S in your transfer function, then you're still expecting to have 0 steady state error. It means that you better have an integrator in your controller so that it becomes 0 steady state error. Make sense? Think about that. I'm going to give you some homework after we explain this. Okay. So, back from this step to this step. So when we are having this one, the transfer function becomes 2 kps plus ki s squared plus 1 plus 2 kp s plus 2 ki. Any questions so far? Is that straightforward? Yes.
为什么 S 在分布 error 这个地方？
因为这个要从中值定理来算。你用中值定理的话，
那它如果 input 不是 step input 的话，是不是这个不算？
对，
所以一定要是 step input。
对，对，我们讲的这个东西全部都是 state input， 只有在 state input 的时候，你才可以说这个积分器会让它为零。如果你是 sin、cosine 这种东西的话，它不一定跟得上。我们这个问题我等一下再回答你，因为后面会有讲到一个 system type， 他会跟你讲说，如果你要 zero steady state error， 它会有不同 type。如果你是一个 step input 的话，你一定要有一个积分器。如果你要这个样子的话，你就一个积分器，它永远会有一个误差。OK， 这个我们之后再讲，马上就会讲到。OK，let's wait for 20 minutes. Then we're going to explain this part. Okay. For now, we got something like this. Okay, and we got our conditions. Zeta equals 0.707, ES equals to 2 seconds, and we got our system with one integrator. So this part has been fulfilled. What is the order of this transfer function? Second order, right? So when we have a second order, what is this one? 2 theta omega n. What is this one?
omega squared.
Omega n squared. So on the other side, I got my W ratio equals 0.707. I got my 4 over theta omega n equals to what? 2, which means theta omega n equals to what? Right? And theta has been identified, which also yield omega n equals to 2. Omega n equals to 0.828 radians per second, which also means omega n squared equals to 8. So then Ki equals to 4, Kp equals to 1.5. So your controller is going to be 1.5 plus 4 over S. That will be the answer. So why do we call this one pole placement? This one over here is because over here, this is my closed loop transfer function, right? And can we determine where my pole where I'm going to put my poles? I can't, because what is a pole location? Pole location is do you guys remember this thing? When we are doing this one, we say the pole location is going to be you guys still remember this? That is something we talked about last time. So if you know your damping ratio, you know your natural frequency for a second order system, then we should be able to know where my pole is going to be located. In other words, if you specify your damping ratio, your natural, your settling time, you are kind of identify where you want to have your pole to be located. Okay? So when we know where we're going to put our poles, put them together, I got my transfer function. Based on the transfer function, we are identify what is my coefficient of my controllers, Ki and Kp. Then, if you put kind of like match the number, if you match the number correctly to the desired performance, we got our controller precisely to have the response we desire. So, with this method, we call it pole placement. It can be used for the second order, third order, or higher order. In this example over here, we're talking about second order. We also talked about dominant systems in the previous example, right? So if you have higher order system, let's say eventually your system is going to be look like this. And you know it's going to be second order dominant in your system. This one over here is part of your controller. What are you going to do? If you know this part is going to be dominant, then just do whatever we just did to fit A and B and your Kp and Ki, whatever coefficient you have in your system. Now, over here, do you guys still remember? In order to make this one dominant, what happened to this one? Faster. If this one can be 5 times faster, then we say this is fast enough to be dominant by the second order system. In other words, use this one over here. 2, 3, 4, 5. If you put your pole of the first order system over here or even further away, then the system is going to be dominant by this pair of poles. Okay, that's just numerical analysis, and we learn how to analyze transient response. First order system is going to be an analysis in this way, and second order system is going to be analysis in this way, depending on which one is dominant. If you say the first order system is not going to be a dominant one, the second order system is going to be a dominant system, then you need to put this pole far away. If you say this is going to be dominant, and these two are going to be not dominant, switch this one 5 times faster, then your system is going to be good enough. In other words, if your system is not second order, it's like 8th order or 12th order. Is that normal? Yes, it's normal. When you are dealing with some kind of acoustic system, sometimes the order can be more than 100. But you don't need to worry about 100 order system, because you can just put most of the system far away, and that the dominant system deal with the dominant system. That's good enough. Okay, is that clear? Everybody understand what I'm talking about? Yes. Pole placement means that I'm going to decide where I'm going to put my poles. If this is going to be a dominant one, then I put my poles based on the calculation. So I know my omega and I know my mean ratio. That is how I decide my pole. Okay, then if I need to have something faster, I just put the poles far away. That's another pole placement. Yes.
它最后还是没有一堆的，一堆的在哪里？
This is an integrator. As long as it's in the denominator, it's an integrator.
如果没有到5倍的话，会是如果他们相差没有到5倍。
Then I'm going to fire you. You need to, because that's一个好问题。一般来讲，我们希望它达到5倍。如果是2倍的话，你的 system 会有 errors。就是你听收音机的时候，你调到譬如说100.7 ICRT 这种，但是你同时旁边有人在拿麦克风唱歌，他的 frequency 刚好在附近，然后我就听到他接收到 ICRT， 然后他自己唱歌的声音，然后你就很说为什么听到很难听的声音，那就是 alias。OK， 在你那个不应该出现的地方出现那个信号就会出现，就为什么要 5 times faster， 就是要避掉这种事情。那个东西在我们这门课不会解释，因为那是 digital control， 那是数位的问题。那一般来讲 ，5 times faster 是必须的。而且我们希望实作上，我们希望它是20 times faster， 因为它够快，5 times 是最少。那没有定律，也没有定律，那只是我们建议值。但是你至少要5倍，低于5倍的话，你的系统会比较失真。如果4倍有没有关系，取决于你老板要不要 fire 你，他心情好不好。心情不好的话，你明天就走路了，就这个样子。那如果你是我的研究生的话，那你去找另外一个老师就可以了。Okay, any question? Okay, now we learn transient response. We learn pole locations. We're going to do a little bit further analysis. But this is more generic. So I got things like this. I got real S's, I got imaginary S's. I got positive side, I got negative side. So at this moment, everybody should know which side is stable. Left hand side or right hand side? Left hand side. This side is stable. When you have your poles located along this line, what does that mean? Critically stable. Because it's sine wave or cosine wave where you have everything over here. So with those concepts, this is left hand side plane. Left hand side plane. This is right hand side plane. If you see your textbook writing down LHP or HP, it means left hand side and right hand side. Okay? If you have your poles located over here, what is the system response you're going to look at? When you have your pole as real numbers, is that first order or second order?
First order.
First order, which means you're going to see your system look like this. Which one is faster? This one or this one? The left one. So you're going to see it's going to be like this, and this one is going to be like this. You don't need to copy this one down, it's over here. Okay? If you have your poles located over here, then again, which one has faster frequency, upper one or lower one? Upper one. So you're going to see this one, lower one over here, like this. When you see things over here, you've got second order. So it's going to be look like this because your real part is still in the left-hand side. So you're going to see something like this. Over here, this one corresponding to the frequency, this one corresponding to decay time. But if you have everything on this side, what happens? If it's over here, this one is going to be step input, right? Because when we do final value 0, you got a step input. What is that? Okay, so if you have x over here, then it's going to be something like this. If you have that in your real x's, what happens? This one over here is going to be divergent. This one over here is going to be divergent, but since this one is larger, so it's going to be what? Faster. Same over here, it's going to be divergent. Depending on whether it's here or it's here, the frequency is going to be a little different. But when you look at the your transfer function and you know your pole 0 located, your poles located at certain places, and you have multiple poles, you should be able to analyze what the system is going to look like and how the poles is going to be look like related to other pole in your systems. Does it make sense? Is that clear? Everybody understand what I'm talking about? Am I going too fast? Yes. Really? I think I'm behind already. Because if you check your textbook, if you check the syllabus, we should be talking about stability right now. It should be topic 6 now, but we're still in topic 4. Okay, let's take a break. Explain. Now, we know if we have something on the right hand side, it's unstable. On the left hand side, it's stable. Let me ask you a question. Is this system stable or not stable?
Not stable.
Not stable, okay. Is this stable or not stable?
Critical.
Okay, critical stable, whatever. How about this one? Is that stable or not stable?
Stable.
Oh, okay, stable. Is this system stable or not stable? Stable. After I design a fantastic controller, this system becomes stable. Not stable. Tell me the answer. This is not stable because this one can be stabilized. Yes, you can stabilize the system. But if you try to do something like this, system remains unstable. Reason is, if you have unstable pole, zero cancellation, sometimes your system is unstable internally. this, though mathematically everything is stable, but internally it's not stable, then system remains as unstable. Okay, so unstable or zero cancellation.
He said. What he had just said.
And not stabilize. Unstable. This is important, okay? And if you see some people doing something like this, and you're the boss or you're the team leader, you should fire the guy. Okay, seriously, that will be something important. Yeah, we're going to talk about steady state error and system type, and that will answer the question what we want to have S in the system. 1 over S in the system, so everything becomes 0 steady state error. Before we start, review one thing, 1 over S 0. Okay, so I got my system like this, closed loop transfer function. G is my plane, C is my controller. So this is what E. What does E stands for? Error. So when we have E of S, it is going to be 1 over 1 plus CG. If you do run the transfer function calculation, block diagram algebra, you should be able to find out what my ES is going to be something like this. So when you design the controller, you have a robot over here, you got a driver, joystick on the other side. The goal is to make this side identically going through the trajectory on the other side. That's our goal. Right? Not only goes when it's infinite, it's going to be 0 steady state error. We hope it's going to be in the very beginning. So if we have something like this, you should be able to identify what is the transfer function of your system. So when we have something like this, there is no guarantee your R is a pulse input, impulse input, or it is a unit step input. It can be other inputs, right? It can be sine, it can be cosine. When we are talking about control theory, we worry about 3 different types of things. The first one is step input. RT equals to 1, which becomes RS equals to what? 1 over S. In other words, I'm looking for something like this. Okay? If you have a motor and you try to drive your you put a motor on the elbow of a robot, are you going to use unit input? You won't, because if you say I'm going to do unit input, it means that my robot can only rotate to this angle, then it stop. Right? You want to have this one gradually move at a constant speed. So we are having ramp input. What does this mean is I got T is proportional to the T. So it's a function of T, and it's going to be first order approximation, so it's going to be linear increase. When we have something like this, R of T equals to T, which means R S becomes what? 1 over s squared. That's the second. Sometimes we want to have parabolic input. Which means I'm going to do higher order. In this case, I'll have squared. Okay, so RT equals to T squared over 2, which means my R over S is going to be, we barely use this. Normally we are using those two, but this one is for some other purpose. I'm going to show you system types. So just keep in mind, you've got those kind of things. You've got the RT equals to units, RT equals to step input. You've got the ramp input, which is proportional to the time, and you might have a higher order. It can be second order, it can be higher order. It doesn't matter. So when we have those kind of things, what are we going to do? So far, any question? Okay. So go back to the transfer function we have. The closed loop transfer function is going to be look like this. And what is the result we want to have? We want to have our error signal to be 0 in the infinite time, right? And the input can be either step input, can be ramp input, can be parabolic input. So it means that my E of S, that's on the other side, is going to be 1 over 1 C G, something like this. Let's just simplify everything to make E of S equals to 1 plus G of S R of S. Okay? I lumped both C and G together as a single function. You can say this is CG, doesn't really matter, but eventually this is something we're going to have. Okay, it's just a transfer function lump in C and G together and put another. Let's put this there. Okay. So when we are doing something like this and we try to find the final value, the steady state error, what do we use? We use what? Final value 0. That is going to give us nothing fancy. Everybody understand what I'm doing right now, right? So what can we do? Which means if you have S close to 0, 1 won't be affected. The only thing going to be affected is function of S. Any question? So let's say this one has its final value, and this value is going to be Kp. Then plug back into this equation. I got 1 plus 1 Kp. That is for my step input. I think in your notes there is a part talking about step input. Any questions so far? I think the derivation is kind of easy. Everybody should get this part without any problem. as long as you know, I simplify g of s when it's close to 0, it becomes a constant. Now, go for yes.
那里面的 E of S 长怎样？
啊？哪里？
就是这上面，
就这个。
没有，我就说为什么 E of S 是那样？
啊？
为什么 E of S 是那样？
这个为什么这个？
就是为什么是那样
？Because if you do something over here, you're going to find E equals to R minus Y, and Y is going to be 1 plus CG. Right? So if you put this one back to this one, you're going to find E equals to 1 over 1 plus CG. That's from your plot diagram. This is from your plot diagram. Okay? Now, go back to the question why I need to have S over here. So in this case, again, go back to our definition. When we have a system, what do we expect our system to, what is the steady state error we expect for our system? The best scenario of steady state error is what? 0. How can we make this one 0? Kp equals to what? Infinite. Okay. So when Kp equals to infinite, what should we have? This one is going to be Ns ds. So how can we make this one to be infinite? As you should have what?
ds
0 over here. When you have 0 over here, what should you have? Integrator. Does it make sense? That's the reason when we try to have step input, we want to have an integrator in the system. When you have a free integrator in your system have 0 steady state error. Does that answer your question? Okay. That makes sense, right? But sometimes we do not have free integrator. So when you try to find your steady state error, you just put this one, replace all s equals to 0, and this is going to be your steady state error. Okay? If you do not have any s in your system, integrator in your system, which means does this one has free integrator in the system? No. Does this one has free integrator in your system? No. Since we do not have any integrator in your system, we have 0 integrator, which means we are at type 0. Type 0 means we do not have any integrator. If we do have one integrator in the system, it becomes type 1. Yeah. If we have 2 integrators, okay, good. Okay. So in the table in your notes, you can see type 0, type 1, type 2. That is how many integrators in your system. If you have type 0 system, what happens? This is going to be steady state error. It's going to be 1 over 1 plus Kp. If you are having a type 1 system, what happened to this one? Type 1, which means you have an integrator over here. This one becomes what? Infinite. When this one is infinite, what is your steady state error? 0. So type 1 for step input is going to be 0 steady state error. So the table, I'll going to build the table later. So if you have type 2, type 2 means how many integrators we have in our system? 2. If we have 1, it's going to be infinite already. If you divide it further by another 0, what is going to be changed? Still infinite. So the steady state error is still 0. Does that make sense? Everybody understand what I'm talking about? Okay, good. Okay, so that is something I explained earlier. So for the second part, I have U naught.
看样本而已。
一加4聚分体，然后就变成1加
What is
4
rep?
这一层。
Rep is this thing. So which means my ESS steady state error is going to be since S equals to 0, what happened to this part? This one is going to be 0. If we say that if we define this part over here as AV, then this becomes 1 over kV, which is the steady state error for rep input. Make sense? Now, if we have type 0, what is type 0? We do not have integrator in our system, which means, can you cancel out the S over here? So if you cannot cancel out the S over here, what happened to this number? 0. When this is 0, what happened to this part? Infinite. Infinite. If we have type 1, which means this one is going to be cancelled out from this one, then it becomes 1 over kV. Right? Because S can be cancelled if it's type 1. S is going to be removed. Then if we do limit, limit is going to be kV just like what we have over here. Make sense? How about type 2?
0.
Type 2 means how many integrator we have in the system?
2.
2. So this one is G2S multiplied by S squared over here. So what happened to this one? Infinite. Infinite, put infinite over here. What is my error?
0.
0. Is that clear? Everybody understand what I'm doing? Very straightforward, right? If we have parabolic, so this part becomes what? 0. So the only thing you need to consider is this part, which means or in your textbook you're going to find out this is 1 over Ka. Now the question is if I have type 0, which means I cannot cancel out this one at all. What is my error? Infinite. If I only have one integrator,
Infinite.
still infinite. If I have two integrators, 1 over K. So this is how we use the system, how we define system types. And depending on the system types, you know corresponding to whether it's unit step or unit ramp or unit parabolic, whether we're going to have 0 steady state error or we don't. So if you want to have zero steady state error for a step input, how many integrators you should have in your system? And this one. If you got one integrator in your system, then you should be expecting 0 steady state error in your system. That's the reason when we try to design a controller for unit step input, we always need to have one integrator to guarantee our system won't have any steady state error. Physical. No, mathematically. Does it make sense?
对，错，这两个小分子把这两个这两个另一个张表。
那我走前面一样轻。
因为这两个把大家都不一样。
一样这样。
目标。你说这两个合起来变成一个，然后你这是C一样
OK。What is a physical integrator? We talk about a lot of things. We talk about mathematics. We got the integrator, so everything is in maths. So physically, what is that going to look like? Any question about any suggestion? I know you guys won't give me any response because you guys are typical Chinese students, so there is no response. Never mind. So let's talk about this. Of course, my girl is not integrated. It's older. Okay, so when I push a button, what happens? When you measure those kind of stuff, it will what? Keep on rotating, since this is a battery. So the output, what is the output? Is the output going to be velocity or position? Or motor? You push this one, well this one start to rotating. So when it's rotating, your constant voltage output is going to get constant what? Velocity or position? Velocity. So the output is omega. Is voltage. Do you guys use optical encoder? No? Okay. Optical encoder is going to be something like this. It's measure how much angle this one is rotating. So when it starts to rotate, the output of this sensor, this is the sensor, which is going to tell you theta. So this is omega, this is theta. What are the relationships? Omega is a differentiate of theta. So if you are reading the theta, what do you have? Are you integrating?
Differential.
No. Omega 积分还是 the theta. So the sensor over here is a what? Integrated. So this is something you can think about when you are doing physical. When you have a motor, you are generating angular velocity. But if you try to use a sensor to measure the position of the shaft, that is going to be the integrator. In other words, you got a controller, this is something you need to design. What is my Y? Right? If I just put something like this is going to be omega, and this is going to be angular velocity. But if I put a sensor in front of this one, and this is an encoder, what am I measuring? I'm measuring theta. So this one over here, it might have a gain, but no matter what you have, it's going to be an integrator. So if you are control this part, it's omega. But if you want to read its position, you need to find a sensor which is an integrator. So when you are trying to find integrator, you need to think everything physically. What you got? This is the easiest way of thinking about that. You got a velocity. If you are measuring something which is acceleration, then in order to measure what, you need to integrate velocity, right? Acceleration. Integrate acceleration becomes what? Velocity. Integrate velocity becomes what? Position. So those are the things you need to think about when you are putting everything all together. How are you going to put everything mathematically to make a physical meaning for you? Make sense? Think about that. I know it's a little bit difficult to think about right now, but those kind of stuff is something you need to understand when you design a physical system. Any questions? We finished topic 4 already. Then we're going to move to topic 5, introduction to PID control. Some of you guys heard about PID control before, right? PID control is a very typical type of control system we do in industry. To be honest, almost everything is PID control. And even though you do not understand what they're talking about, people still use PID control. Now we're going to talk about what is a PID control really look like. Okay, so but before that, let's start something. this is the most typical block diagram you guys is going to see in the future. Though we simplify a lot of things using G and H only, but this is really something you need to know about in a real system. Though, okay. So we got R. This is my reference. Let me explain this one more clear, because we're going to deal with control system from now on. It's no more mathematical only. So this is reference, which means this is my desired signal, and this is my output. This is disturbance. So this part over here is physical disturbance. It can be anything that pushed by my girl, pushed by a dog, anything. And when you got external force, that's considered as disturbance. And of course, we got controller. We got our plate. So those are the things we talked about earlier. H over here is the what? Sensor. In this part, I add two more things. One is N. This means I got noise in my system. Noise is different from disturbance. Disturbance is physical input. You might have force, you might have something that actually affects your system. But the noise over here is because you put the sensor over here. Sometimes you just measure something random. That is going to be considered as noise. When you have a noise, it's not physical disturbance. So they need to be separate a little bit, okay? And you find another one over here. This is something we call feed-forward controller. This part over here is something we call feedback control or closed loop control. When you have a feed-forward controller, this one is taking the R and shape the geography graphically of your input data, because when you have a natural frequency in your system, you guys know, I believe most of you guys watched the video that you see the Golden Gate Bridge in San Francisco. When they have an earthquake, they start to vibrate larger and larger and eventually destroy the bridge. Right? You guys saw those kind of video before, right? So it means that if there is something bad to your system and you know its frequency, probably we don't want to have the signal get into the system. Therefore, we are going to have a feed-forward controller or a filter. Most of the time, we prefer to say this one is a filter, to take out those undesired signals from the reference. So it's going to be a feed-forward controller in front of everything, but actually this is just a filter. Okay. So when we consider everything all together, that is going to be my control system. In many cases, we do not consider this part in this class because this is really not something we need to worry about when we are designing a controller. So when we are having everything all together ready, we start to block diagram calculation. So my y of s is going to be 1 plus GP R of S plus So far, nothing fancy. You guys deal with this thing earlier, right? You got two inputs. One is reference, the other one is disturbance. And we talk about if you want to have your controller, if you have a controller which is large, then you should be able to get rid of the disturbance, the effect of disturbance, right? But this time, it's going to be different because we got the noise. So there is one more block. needs to be identified. Okay, so this time, based on this configuration, we got 3 inputs: reference, disturbance, and noise. And over here, it is going to be like this, but you can also consider this one as so I have 3 outputs. Since I have 3 inputs, I'm going to have 3 outputs. The overall output is going to be a combination of this one, and this one. So when you are designing your controller, what do you expect? This one, when time equals to infinite, what should I have this one? Equals to what? No, it's not here. It has nothing to do with final everything. Huh? Should be what? This is my output. So when time goes to infinite, what does this one should be equal to? Good. It should be off. That's your goal. Because you have a robot. You hope your robot exactly doing something drive it. So this one should be off. How about this one?
0.
Very good. How about this one?
0.
Good. So eventually, we hope to be something like this. So if we are talking about GC as if my, let's talk about something basic. It's just a K. This thing is called P controllers. Okay, so what happened if you want to have this one equals to YR of S? Huh? By looking at this one, so in order to make this one equals to 1, what do I need to do? There is only one thing you can control. You cannot change anything about the plane, right? It's when you have a motor, it's a motor. You cannot say, okay, I'm going to tear that thing apart and change the motor. You cannot do that. You got a sensor. The sensor, you buy that from the company, and you won't be able to change anything. So this thing cannot be changed. Feed-forward controller is in your system as well, so you cannot change that at all. So what can you change? K. So how can you make this one to be 1? You can make K becomes what? Large. If GP multiplied by H is 1, GF multiplied by GP equals to 2, but K is 1,000 or whatever, what happens? K is dominant, the whole thing, which means it's going to be, when you have high gain, which means K is large. Your YS is going to be the same as your input. High gain system is always like that. We're going to talk about whether high gain system is a good one or not good one. It's a good one because it's going to be something like this. It's a bad one because there are something else we need to worry about. But when we have high gain system, it always guarantees your system is the same as your reference. But is that always true? Because when you increase your K, it also changes something over here. So let's talk about this thing. So if you increase your K to almost infinite, to almost infinite, what happened to this part?
0.
0. So great.
Yes.
I can reduce the effect of disturbance. Very good. So we decide to use high-gain system. Is that true?
No.
Of course, if I'm asking, it's not true. Why? Because so if your K is infinite, what happened? Right? So it means that if you have your system like this, you've got a high-gain system, you are going to have good tracking performance because Y is going to be close to R. You're going to reject disturbance because this part is almost 0, so you're going to reject almost all the disturbances. However, when we talk about the noise, since K is existing at both numerator and denominator, you increase the K, you are guaranteed or you secure your R. Meanwhile, you secure your noise. So everything becomes R plus noise. So if your noise is pretty bad, your system is going to be having a lot of noises. So in some words, this is not good, right? So how are we going to deal with this one? What is noise? When you listen to a radio, what kind of noise are you going to have? Is that going to be low frequency or high frequency? High frequency is always something like a background noise, and it's kind of high. In some case, you guys can hear that, and I can't because I'm old and used to it. Seriously, after 28 years old, you're going to feel you become old. Seriously. So when we are talking about those kind of things, the S over here is going to be what? J omega. I think we talked about this one earlier, right? So omega is what? Frequency. So if you got noise, you know your frequency of the noise is always high. And your reference over here, since we are mechanical engineering, so everything related to motor, as long as you are not dealing with something extremely small like nano or micro, then the frequency of the motor should be about 40 hertz, no more than 200 hertz, no, most of the time. So if you can have your gain low frequency, high frequency. So if you can have your low frequency to have high gain, but you have your high frequency with small gain, that is going to be eliminate this part and keep this part. So that's a design phenomenon that we're going to have for PID control. Does that make sense? I'm out of time. I'm behind. Any question before I let you guys go? Is that clear? So over here we're talking about the gain, and next time we're going to talk about P controller, I controller, and D controller. Okay, and they have their physical meanings. And we're going to talk about mathematical meanings and physical meanings. And when we put everything all together, what it's going to look like and how it's going to affect your system. So you please bring a copy of the notes if you haven't downloaded it, because there are a lot of figures. I would prefer you guys look at the notes instead of drawing over here. Some of those I cannot draw because I use MATLAB to simulate. Any question? Okay, I'll see you guys Friday.